Well, and if you'd been looking at your guide, you would have seen Scott Cole's the presenter, and although we are nearly indistinguishable from one another, except for maybe a foot in height difference, you got me. So I'm Leslie Wood. I'm a senior scientist.
I can tell the difference.
You can, well, it's hard, but you're good. Yeah, I'm Leslie Wood. I'm a senior scientist with Visionary Fiber Technologies. We're a technology innovation company located in Lockhart, Texas, which is like a 20-minute drive south of Austin. And at our facilities, we develop and commercialize processes around our core technology, which is the fiber reactor. And one of those that we've developed, I'll be speaking about today, which is utilizing immobilized enzyme, in this example, phospholipase enzyme, on the fiber reactor to effectively pretreat soybean and DCO for renewable fuels. But I mean, you know, in the case of soybean, it could be used for edible uses as well to replace the typical degumming step. So first of all, I need to explain, you know, what a fiber reactor is. Hopefully many of you have come by our booth by this point or have seen Scott's talk in the previous session. Essentially what it is we construct a fiber bundle using many fine fibers or filaments or wires, however you kind of want to think about it. And the filaments or wires that we use are very, very fine, tens of microns in diameter. And we assemble that as a bundle and we pull it through a conduit, and effectively we've created a microchannel reactor. And in doing so, we allow these immiscible phases. In this example to the left, we have this dyed video to kind of give you a visual understanding. We have the water phase in blue and the oily phase in yellow, and they're able to kind of glide past each other, and the dissolved solutes that are contained therein can then transfer from one phase to the other without, as in the example of traditional mixing, you know, consuming more energy to churn those two immiscible fluids together and, you know, perhaps creating intractable emulsions. And specifically for what I'm talking about today, in addition to having this microfluidic effect, we've also immobilized phospholipase enzymes on the fibers so that they're right at the interface of where that reaction occurs at the oil-water interface. And that's why I think, you know, we're able to do this so quickly relative to stirred systems, whereas in this other example here, you know, you create these big droplets in a continuous phase and your surface interfacial contact is limited by that. So another aspect of the fiber reactor relative to like a packed bed system that contains spherical particles, if we compare the pressure drop that we see in a column of the given dimensions here, a little under 1 meter in height and about 25 millimeters in diameter, internal diameter, and we fill that column with either 50 micrometer diameter silica beads, spherical beads, or in the case of the fiber reactor, we have 50 micrometer diameter fibers, and we run peanut oil through that column. As a function of flow rate, we see the pressure drop. The dashed line is for the packed bed column, and that's just a simple calculation, a theoretical calculation. And at the bottom, we see the dark line is the VFT column, and that's actual collected data. But, you know, if we look at the flow rate and we just go kind of like to the highest or fastest flow rate that's recorded here for the fiber reactor, at about 900 mils a minute, we're sitting under 3 psi pressure drop, whereas the packed bed column is above 300 psi. So we're able to achieve very high throughputs, and as opposed to the packed bed that has this more tortuous path, and those spherical particles being able to pack more tightly, we're still having these channels that run the length of the vessel, and so our fluids can glide through much more efficiently. So we're talking about pretreatment, right? And in large part, you know, if we're using enzymes to do that, we're talking about the phospholipids and the associated metals. Many of you are probably well aware of the phospholipid structures, but let me go ahead and run through this so we're all on the same page. We have the ball and stick model on the right there. The top image is a general phospholipid structure. We have the glycerol backbone, and attached to that we have 2 fatty acids, denoted in this case by R1 and R2, those gray spheres. And then at the other end of the molecule, we have the phosphate, and then the head group, denoted by R3, which could consist of a few different versions, choline, ethanolamine, inositol, serine. And then in the case where we don't have a head group, we just have a phosphatidic acid, and that's shown in that below stick ball and stick model. In that case, we have these negatively charged oxygens that if they run across a divalent cation, they will bind to that cation, and those become very difficult to hydrate. So to the point about hydration, well, first off, if we just look at soybean oil extracted as an example, in that very small table at the top, you see kind of general numbers for crude extracted soybean oil, quite high in phosphorus and associated metals. If we look at the table to the top left here, we see general ranges of distributions of those various types of phospholipids that can be found in the soybean oil. And so primarily you're going to find the phosphatidylcholine ethanolamine species, followed by inositol, phosphatidic acid, and the serine. Now, the reason why that's important is because they all have different rates of hydration. And the faster they can become hydrated, the more quickly they can be brought into the water phase and taken away from the oil. So phosphatidylcholine will hydrate much more rapidly than all the others. And then you see the relative rates followed by inositol, ethanolamine, phosphatidic acid, and then those phospholipids that are coordinated to the divalent metals even much more slowly hydrating. So for a given crude, you may have more or less of these difficult to hydrate phospholipids, and then that oil becomes much more difficult to treat. So then we bring in enzymes, which the reason we'll use these phospholipase enzymes is that what they do is they cleave or they break bonds at certain parts along this phospholipid body. And in doing so, the compound that remains is much more water soluble. So there's a few different types here. The PLA1 will cleave at the SN1 position, and it will liberate a fatty acid and a lysophospholipid. PLA2 will cleave at this 2 position, and again, liberating a fatty acid and a lysophospholipid. PLB can cleave at either, but its primary substrate is a lysophospholipid. The PLC will cleave at this bond between the phosphorus group, and finally PLD at the head group. For degumming, we're usually using PLA or PLC. It should be mentioned that when the PLA will cleave at this first position, the resulting molecule is a little unstable, so we'll typically get a acyl rearrangement from the 2 to the 1 position, and then in theory that enzyme can cleave that yet again and create a glycerol phospholipid. Whereas the PLC, where it cleaves, you'll create a diacylglycerol, a DAG, and then the phosphate head group. So oftentimes these enzymes are used in conjunction or one or the other. It really kind of depends on your goal. But the PLA will get the phosphorus count much lower because it can act on all these different phospholipid types. But the PLC is selective for the choline and the ethanolamine, not for the phosphatidic acid or inositol. So typically, the PLC won't get the phosphorus content quite as low. And then PLD is just something that processors have to deal with because at certain temperatures, it becomes more active. So as they're extracting the soybean flake, if that's not well controlled, this enzyme will run around cleaving head groups and creating more phosphatidic acid and then creating a more difficult to treat oil. So before I go into some of the results that we achieved, I just want to kind of show, this is kind of collection of enzymatic stirred results from literature. And there's a lot to look at here, but essentially all I'm trying to highlight is, first of all, the stir time that people use. It's like 2 to 6 hours, generally speaking, and then the final phosphorus value that they achieve after the enzymatic process, typically below 10 part per million. And in general, at least all the references that I've come across, a citric acid or some other kind of chelating acid pretreatment step will be used ahead of the enzymatic treatment. So typically by the time you're coming in to the enzyme treatment, you might be sitting around 50 part per million phosphorus or something like that. But of course, it depends on the nature of the crude oil you're working with. So here's just a really kind of simple schematic of how this is done in stirred enzymatic processes in industry. So you've got your crude oil coming in. It'll be dosed with a certain amount of, I mostly commonly see people using citric acid. That'll stir at temperature, maybe like 80 C for, 15 minutes to an hour. I'm sure it varies from plant to plant. And then that oil, after that step, will be cooled to about 50 C because You can't interact. I mean, the enzyme will become degraded at too high of a temperature. And you also will do a slight pH adjustment with caustic to bring the pH of the aqueous phase to the appropriate pH of the enzyme. If the pH is too low, the active site of the enzyme can become protonated and therefore not functional. And then at that point, they'll add the water, the additional 2 to 3% generally, water and the enzyme. It goes through a high shear mixer, again, because they have to create that interface and chopping up those water bubbles as finely as they can, and then going into a long stir mixing for 2 to 6 hours and typically hitting below 10 part per million phosphorus. The way VFT conceives this is that we still use the pretreatment step, and when I say pretreatment, I refer to the citric acid or phosphoric degumming step up ahead. And then we pH adjust to about 4 to 5, cool the oil to 50, and then with the additional 2 to 3% water relative to the oil, that flows through an enzymatic labeled column. And at least in the study that I'll show you on the next slide, on average, we are getting below 8 part per million phosphorus from that one pass. And we find that if we send it through a second enzymatic reactor, we're now generally below 3 part per million. And what I need to emphasize very strongly is that the transit time through the fiber reactor, it's a continuous process. A unit of oil goes from the top to the bottom in under a minute. So what takes stirred reactions multiple hours, we're able to affect in less than a minute. And if you need to drop those values lower, or if the oil is somewhat harder to treat, you just kind of add another column. You're not adding any more chemical, you're just passing it through another enzymatic column. So one thing we needed to know once we realized this worked was, okay, well, how long is the enzyme going to remain active? So to do that, at least to some extent, we were able to source a crude extracted soybean oil from a producer, and we assembled a little test pilot at our facilities where we would pre-treat with citric acid at 80 C for 15 minutes, then cooling the oil to about 50 and pH adjusting between 4 and 5 with base. And then that, along with the 2 to 3% added water, was passed through the fiber reactor. And again, transit time under a minute. What we found over continuously running the system for 37 days was that the one pass was on average 7 part per million. And you can see in that table below, the crude was just under 600 ppm phosphorus. And then after pretreatment, just as a reference, it was around 50. So similar to some of those cited values that I showed earlier. Every day we would come and we'd draw from the lines just before the fiber reactor and just after the fiber reactor, and then tracking by ICP, trying to see if at some point over that course of time, all of a sudden, the impurity levels were ticking up higher. And we did not see that. And so from that concluded that it had remained active for that point in time. Here's another example of when we were treating a different crude soybean oil from that same producer, starting off quite a bit lower, but the phosphorus around just under 240 ppm, and you see the associated metals there as well. So we compared 2 fiber reactor columns, one labeled with PLA1, one labeled with PLC. The PLA1 gets everything below detection in one pass. We also were doing the citric acid pretreatment. But so the only thing remaining in the PLA version was a small amount of potassium versus PLC. We had the phosphorus remaining at around 13. And then if you add up the remaining metals, they're kind of 1-to-1 with the phosphorus. So probably a lot of the remainder was phosphatidic acid. And as we've already kind of discussed, the PLC does not select for that phospholipid. And so it's not surprising that it didn't get that phosphorus value quite as low. Here's one example for DCO. The phosphorus starting around 350 ppm, and you see all the associated metals there. In this case, with the citric acid degumming and the one pass through the fiber reactor labeled with PLA1, the phosphorus is around 7 and potassium just under 4, with all the other metals dropping to below detection by ICP. So one thing that I noticed very early on as I was doing this work is the nature of the gums that are produced when you use this enzymatic process. especially for the PLA1, take on a very different consistency. They're very loose and mobile. So here's a few different images to kind of give you an idea of that. In the top left here, if we just compare the acidic pretreatment, you see the gums that are settling out there and very darkly colored because they're in training oil. Now, to be fair, at this point, when you do the citric acid pretreatment, you're dosing concentrated citric acid. You're really only adding about 0.3, 0.4% water relative to oil at this point, which is part of the reason why they're so kind of entrained. But once it goes through the fiber reactor with the extra water, you see those gums crashing out and giving up their oil. Another example, just below that, we see these test tubes. And so if I take the crude soybean oil and I just centrifuge, you see the nature of the gums on that first vial to the left. You know, it's slightly orange and it's in training oil. If we spin down the citric acid pre-treated version, again, we are crashing out more solids now, but they're also still entraining that oil. If I take that citric acid pre-treated material and I do a standard PLA enzymatic stirred process, we see that in the third vial over. And those gums are much more light in color because they're not entraining as much oil. But now, if I take that pre-treated oil and I run it through a PLA labeled fiber reactor column, you see that originally that vial to the far right, it had gums spun down to the bottom of that tube. But as soon as I lay it on its side, they slide back into the tube because they have this loose consistency. And so another example, we see these jars at the top of this slide, and we were kind of looking at different temperatures, trying to optimize. But suffice it to say that I took some crude soybean oil, I pre-treated a big batch of it, and I had a fiber column here and a fiber column here. And this fiber column had no enzyme, and this fiber column had the PLA enzyme. I did one pass of that pre-treated oil through that column. I collected in those jars. I set them on the bench top. And you see the way they settle in time. The one that has the PLA enzyme settles out much more effectively, giving up its oil, and that's a function of those phospholipids being cleaved. So, and lysophospholipids in and of themselves are, another value-added product. One thing that I did come across in literature, and I don't know how much of a problem this is for people in general, but I read that, because you're creating lysophospholipids, and lysophospholipids are a great emulsifier. I mean, if you're stirring something for 2 to 6 hours, you could create some nasty emulsions for yourself. But because the fiber reactor principles and the way that it works without these high shear events and transiting in under a minute, we can deal with these lysophospholipids without creating a difficult to, separate oil. And finally, this is just building on the last slide, but the one to the left is no enzyme, and the one to the right is the PLA fiber reactor enzyme. And if you look carefully, so these were spun down, right? So at the bottom of the tubes is the whitish part with the gums. And as I rotate the vial side to side, the one that did not have enzyme on the fiber column, they just stay put. They stay stuck. Whereas if you look at the one that had the enzyme, you can see the whitish material kind of slosh up and down the sides of the vial as I tip it right to left. And again, that's just, like I said, they have this different kind of, loose consistency. So with that, I'll thank you for your attention and take any questions.